Assalamu alaikum. In today's tutorial on WIEN2k, we will show how to do SCF calculation using full hybrid potential. In a previous video, we have shown how to use on-site exact exchange and hybrid functional, which is actually the correction for d and f orbitals. Now today we will show how to use unscreened and screened hybrid potential, and this is the full hybrid potential. So let's start. For this calculation, I will use the magnesium oxide structure, and this is the structure of the magnesium oxide. First, I will do the SCF calculation with the PV potential. Then I will use the full hybrid potential so that we can make a comparison of the results. So let's start. I will initialize first. Now I like you to make a note of the KMH details that I am using. That is 10, 10, 10. Now let's run the SCF, run for SCF. So if you see here, there is no extra flag, just the converging criteria. So the calculation has finished. Now let me show you the results, what I get. So I'm in this directory. Now I will use the script get result. So you can see that I have a band gap. The system has a band gap of about 4.75 electron volts, and the potential that I used is PB. Now here I used the get result script. If you go to my website, you will find the video in the related video section which says that extract key information for SCF calculation. In this video, I have explained how to use the get result script and how to get these informations after doing the SCF calculation. Now let's plot the band structure, and you will find the video of plotting band structure in my website also. The link of my website will be given in the description. Now I need to edit this and change this with the Fermi values. That is, I will write 3067. Now let me change the range. Let me choose from -6 to 15. No, sorry, I didn't do the calculation. Okay, here is the band structure, and you can clearly see the band gap is about 5 electron volt. Now let me do the SCF calculation with the full hybrid potential. So I am in the same directory like this one, and before doing so, I will save the results so that I can see the differences. I will use the name PVE. So the results have been saved. Now to do the SCF calculation with full hybrid potential, I need to run this script init_hf_lapw. So if I go here, it says that I need to edit this one, and I need to choose the n band value, which will be greater than occupied n band. Now to know how much bands are there, what are occupied, I will use the terminal. And if you remember, I have changed the name of the file, so I will have only one SCF file, and that will be PV. So I will use grep band pve.scf. Now you can see from here, the up to 8 the bands are occupied. The fourth column is the occupancy number, and I have bands up to 13. So I can use any value from 9 to 13. Okay, let's click here. I will use here 13. Let me give you the description of this file. So if you see here that the alpha value, if I use alpha value is 0.25, and if I use T here, that is for the screen, and then this potential will be YSPV0. This is here, because I did the calculation with the PV potential. You can find all the details in the user guide. So if we go down to the user guide, we will see a section that unscreened and screened hybrid functional. So if I click here, and you see here all the description is given and the list of available functional is given. It says that if I use that PV with in case in.0 with this flag, and the case in 0_GZR with this flag, then the functional will be PVE0 or YSPV0 with alpha equals 0.25. This YSPV0 is similar to HSE0 hybrid functional, sorry 06 hybrid functional, and which you may find in CAS7 or any other DFT calculation packages. So let me show you what I have in in.in0 file. So I will use the terminal, and so you can see I have this flag as described here, and let me show you what I have in the other file. So this is the same as this one. Yeah. Now if I use the T with this parameter, it will be YSPV0. If I use F, it will be PV0. So I'm using here T. So I will save this file now. Sorry, I will use the 12 band. 12. Now you can use even a higher n band value than the total number of bands. In that case, you need to edit this file test.in1. It says here. Now there is one more thing about the using hybrid functional, that the calculation is expensive. This is usually 100 to 1000 times or something like that, 10 to 100 times expensive than the usual PV. But we can reduce the calculation cost by using a lower K mesh. So what I will do, I will use a lower K mesh. For if you see the user guide, it will show you the cycles. It will do the calculation with the usual functional, that is PV first. Then it will do the SCF calculation with hybrid functional. So I need to use, or I need to choose two K mesh details, one for the usual calculation and another for the hybrid functional. And for hybrid functional, I will choose 2 so that the calculation becomes quick, since this is the tutorial purpose only. But when you do the calculation, you have to choose this depending on your system. You may find the details of this in the user guide. Not sure, just need to go to a little bit up. Let me see. No. Yes, here it is. How to use the reduced K mesh for a hybrid functional. So you can read this one also. Okay, let's run this one. Now, since I used a reduced K mesh, I need to use red K list flag, which is described here. So I go to the run SCF, and I will use this one. If you do not use any reduced K mesh, you choose the SCF functional. Okay, so I click here. Now the calculation will take time a little bit. So let me pause the recording. So when it finishes, I will be back. Okay, now the calculation has finished. Let me compare the results. So I will use analyze, and I will compare the energy, Fermi energy, and band gap, and I will use all the SCF files. So click here. Now you can see the energy values are very close, but you can see the Fermi values is significantly different because this is in Rydberg. So if you convert it to electron volt, these differences will be higher. You can see here now. This is in Rydberg. So if you see in electron volt, with the PV calculation, PV functional, it was about 5 electron volt. Now it is more than 6.5, that 6.69 electron volt. So since I have now I want to show you how to do the band structure or plotting. So since with this new SCF calculation, I have the Fermi energy is this value. I need to use this one. So and we need to use another command actually. Using the usual command, the band structure will not be for the hybrid functional. But before doing that, let me change this value so that I can. Okay. Now to do the calculation for band structure, we will use run band LAPW. Let me show you what it means. So I use -h flag. Now you can see it says that we need to run this one to do the calculation with hybrid functional, and we need to use the red catalyst if we have used this one for SCF calculation. Since I have used this one, so I will use this one here. Then we need to run this spaghetti with the -HF flag. So let's run this one. It will take little bit time, so let me pause the recording again. I will come back when it finishes. Okay, the calculation has finished. So let me run the spaghetti as it's described here. Okay, now I can plot the band structure. So you can see now the differences between these two. Yeah, now you can see clearly the gap is higher here. So this is all how you do the SCF calculation with the hybrid functional, and how you do the band structure plot when you do the SCF calculation with PV functional. I hope this will be helpful. Thank you.